Let us look at some of the properties of discrete time Fourier transform today. Okay, the properties are what we have studied for Fourier transforms and other Z transforms. Similarly, we have properties for DTFT also. Let us look at them one by one. Let us understand the significance, and after this let us do some problems on them. Okay, let us start with the first property of DTFT. The first property of DTFT is called as the periodicity property. It states that the DTFT is always periodic in omega with a period 2 pi. That is, x of e to the power of j omega plus 2 pi k is equal to x of e to the power of j omega. Okay, now we say that this is periodic with respect to a period 2 pi. So, this is equal to e to the power of j omega. That means, this is the period in which your DTFT repeats, whereas CTFT in general is not periodic. Okay. This is one glaring difference, or generally the most important difference between a DTFT and a CTFT. Let us look at the second property called as a linearity. The DTFT is linear if z of n is equal to a x1 of n plus b x2 of n. Will have a DTFT z of e to the power of j omega equal to a x1 of e to the power of j omega plus b x2 of e to the power of j omega. Okay. So, let us see this linearity property. Let us take two signals, x1 of n and x2 of n. Okay. So, let us say these are the two signals to be added, then this will be your total signal, and let us say this is having a DTFT of x1 of e to the power of j omega, and this is having a transform of x2 of e to the power of j omega. Okay. Then let us say that this is having a transform DTFT of x to e to the power of j omega. Now, when we look at this, either I can use x here or invariably I can use z also here. So, when I use z, then this will be replaced by capital Z here. So, when I add these two, then this also gets added. Now, let us say this is scaled by a factor a and this is multiplied by a factor b, then a linearity property also this is multiplied by the same factor as you see here, this one and this one. So, this is what is called as a linearity property. So, we are so when such type of problems are given, what is it we have to do? First of all, let us find out the DTFT of a given signal separately and then sum them up, so that you will get the DTFT of the total signal. So, this in fact helps us in solving complex problems where you have multiple signals which are getting added up. So, this will help us, this property actually help us in minimizing the complexity of such type of problems. Let us look at the third property. It is called as a time shifting property. So, this property states that if a discrete time signal is shifted in the time domain by n0 samples, its magnitude spectrum remains unchanged. However, the phase spectrum is changed by an amount omega n naught. That is, x of n minus n naught will have a transform, discrete time Fourier transform equal to e to the power of minus j omega naught x e to the power of j omega. So, let us look at this again. So, what does the time shifting property say? Whenever a time signal shifted in time domain by n naught samples, its magnitude spectrum remains unchanged, whereas the phase spectrum is changed by an amount omega n naught. That is, x of n minus n naught is have e to the power of minus j omega n naught x of e to the power of j omega. Okay, let us see this. So, what does this property say? Let us say x of n is having a DTFT, okay, of x e to the power of j omega. Okay, when these samples are shifted, then this property says the magnitude is not changed. That means, this essentially remains the same, whereas the phase, there is a phase shift of minus j omega n naught. So, this is what is the property of time shifting. So, whenever there is a shift here, the magnitude does remain same, whereas the phase is changed by this factor. So, let us just conclude this property. The property says that delaying a discrete time signal by n naught units does not change its amplitude spectrum, but the phase spectrum is changed by minus omega n naught. So, any delay in the discrete time signal by a certain factor n naught does not change the magnitude of the discrete time Fourier transform, whereas the phase is changed by a factor minus omega n naught. That is the factor of change. The fourth property is frequency shifting property. This property states that the multiplication of a sequence x of n by a factor e to the power of j omega n naught is equivalent to a frequency translation of the spectrum e to the power j omega by omega naught. Okay. Since the spectrum x of e to the power j omega is periodic, the shift omega naught applies to the spectrum of the signal every period. That is, e to the power of j omega n naught x of n will have a dtft of x e to the power of j omega minus omega naught. Okay, that is the frequency shifting property. E to the power of j omega n naught multiplied by x of n will have a dtft equal to x of e to the power of j omega minus omega naught. Okay, this is what is called as the frequency shifting property of dtft. Let us look at the next property. It is called as multiplication by n. The frequency differentiation. This property states that when x of n is multiplied by n, it is equal to differentiation in the dtft. That is, n of x of n will have d by d omega of x of e to the power of j omega. That means, a multiplication of x of n by a factor n will have d by d omega of x of e to the power of j omega. So, this is that means, whenever you multiply x of n by n, the discrete time Fourier transform will be differentiation of that d by d omega of x e to the power of j omega. Next property, complex conjugate and conjugate symmetry. So, what does this property say? This property states that we can obtain complex conjugation of a complex discrete time signal x of n by reversing the sign of the imaginary part of the complex signal x of n. That means, x of n, let us say, is having a dtft of x of e to the power of j omega, then x star of n, that is a complex conjugate of x star of n, will be x star of e to the power of minus j omega. That means, reversing the sign of imaginary part of the complex signal, that is what we are saying. So, x of n is having a discrete time Fourier transform x of e to the power of j omega, that is already we know. Then x star of n, that is a complex conjugate x star of n, will have a discrete time Fourier transform equal to x star of e to the power of minus j omega. So, that is what this property says. The important note here is the real part of x e to the power of j omega is an even function of omega, whereas the imaginary part of is an odd function of the omega. Okay. That means, the magnitude is an even function and the phase angle is an odd function. So, that is what we have to understand from this property. Then coming to the seventh property says, seventh property is called as time reversal property. It says that if a discrete time signal is folded about the origin in time, its magnitude spectrum remains unchanged. However, the phase spectrum undergoes a change in sign. That is, if x of n is having a discrete time Fourier transform x e to the power of j omega, then x of minus n, this is a signal which is folded or the sign is made negative, it will have a discrete time Fourier transform x e to the power of minus j omega. This property is called as the time reversal property and is the seventh property of discrete time Fourier transforms. Let us look at one of the most important properties of any transform. So, let us look at the convolution property of dtft. The convolution property is as follows. Let us say x of n is having a discrete time Fourier transform x e to the power of j omega, and let us also have another y of n which is having a discrete time Fourier transform y e to the power of j omega. Then z of n equal to the convolution of x of n and y of n. When I take the discrete time Fourier transform for this, it will be multiplication, that is x e to the power of j omega and y e to the power of j omega. That means, the convolution, let us take two signals, okay, x of n and y of n. Okay. Let us say the y of n is having a dtft of x e to the power of j omega, okay, and y of n is again having y of n is again having a discrete time Fourier transform called as y of e to the power of j omega. So, according to this convolution property, let us say x of n is convolved with y of n, okay, and let us give some name to this. Let us say this is z of n, okay, z of n will be the convolution of this. Then z of n will have a dtft, let us say, that is given by z of e to the power of j omega. Then this convolution will become a multiplication here. That is, this will be equal to x e to the power of j omega and y e to the power of j omega. So, this is what is the convolution property. So, we have to remember this point as we have been discussing so far. Convolution in this x of n and y of n will result in a multiplication or a product when I convert this into a discrete time Fourier transform. This is an important property. Whenever we are trying to analyzing an LTI systems, stable systems like that, this will help us in analyzing the system very well. Let us look at the next property called the scaling property. Okay, let us take a discrete time sequence x of n, which is scaled by a factor p, that is x of p n, and let us call the scaled signal as y of n, where p is an integer. In this case, the information x of n is discarded, then scaling property has no meaning. Therefore, this property is applicable only to those sequences for which x of n is 0 for n by p not equal to integer, then x of n is not equal to 0 for all n values. So, that particular part p must be an integer. Okay, this is what the scaling property of discrete time Fourier transform says. This is the ninth property. Then the data will not be discarded, the discard data due to scaling will be zeros. Then y of n is equal to x of p n will have a discrete time Fourier transform y of e to the power of j omega having equal to x of omega by p, that is n into p, which we are doing in x of n. When I take a discrete time Fourier transform, it will become x of omega by p. Okay? That means expanding in time domain is equal to compression in frequency domain. So, whenever I expand in time domain, that means I increase the time scale. When I take a discrete time Fourier transform for this, it will be compression in the frequency domain. Let us look at another property called as multiplication in time domain, which is the 10th property. So, what does this property say? Whenever z of n is equal to x of n, y of n, that will be equal to z of e to the power of j omega 1 by 2 pi x of e to the power of j omega convolved with y of e to the power of j omega. That means, if I take two signals, let us say again we are taking x of n and y of n. Okay, x of n is having a discrete time Fourier transform of x of e to the power of j omega. So, this is DTFT. So, x of n is having a discrete time Fourier transform x of e to the power of j omega. Then y of n is having a discrete time Fourier transform y e to the power of j omega. Let us say these are being in time domain, there is a multiplication that is happening. Let us take z of n is equal to x of n, y of n. Okay, and discrete time Fourier transform of this is z to the power of e j omega. That will be equal to 1 by 2 pi, okay, x of e to the power of j omega, which is the discrete time Fourier transform x of n, and y of e to the power of j omega. As you have guessed it right, this is convolution of these two. Okay, so, this is similar to the earlier property which you have seen a little ago. Multiplication in the time domain results in convolution in the frequency domain here. Similarly, when I multiply in the frequency domain, it will be convolution in the time domain. So, this is a very important property. Let us look at the 11th property. It is called as Parseval's theorem. What does Parseval's theorem say? It states that the total energy of a discrete time signal x of n may be determined by the knowledge of its DTFT. That is, energy is given by 1 by 2 pi integral minus pi to plus pi mod of x e to the power of j omega whole square d omega. So, this is how you get energy of a signal. That means, to calculate the energy of x of n, if I know its DTFT, that is discrete time Fourier transform, then I can be able to calculate my energy. This is called as Parseval's theorem. Let us see this Parseval's theorem. So, let us say x of n, this is having x of e to the power of j omega. Okay, this is the DTFT. Okay, now this is known to us. So, this is known to us. Now, I want to calculate the energy of this. The energy of this is calculated when I know this. That means, this is the formula as per Parseval's theorem, minus pi to pi 1 by 2 pi mod of x e to the power of j omega, okay, whole square d omega. So, Parseval's theorem, minimum requirement is I should be knowing the discrete time Fourier transform of a given signal. so that the energy can be calculated. The energy is calculated in this way. Let us look at the next property. The energy density spectrum at discrete time aperiodic signals. The energy of a discrete time signal x of n is expressed as E is equal to summation of n is equal to minus infinity plus infinity x of n whole square. According to Parsevals theorem, E is equal to 1 by 2 pi integral minus pi to plus pi mod of x of e to the power of j omega whole square d omega. Okay. So, substituting this, we can say psi of e to the power of j omega I can put as x of e to the power of j omega whole square. So, this represents the distribution of energy as a function of frequency and is known as the energy spectrum of a discrete time signal x of n. Okay. So, what is it we have done? We have taken this psi of e to the power of j omega. This is equal to x of e to the power of j omega, okay, whole square. So, I take this. Okay. This is how we are substituting. In this place we are putting this. So, this is called as the energy density spectrum of a discrete time signal x of n. And if you look at this, this psi of e to the power of j omega does not contain any phase information. There is no phase information available. Okay. Let us look at the final property called as the duality. So, what does this duality say? In discrete time Fourier transform, no duality exists between the analysis equation and the synthesis equation. So, there is no duality that is possible in the case of a DTFT. There is no duality that exists between the analysis equation and the synthesis equation. But there exists a duality in the discrete time Fourier series. Also, there exists a duality between the discrete time Fourier transform and the continuous time Fourier series. So, duality does exist, but not exactly in a DTFT, but as we have just read in those cases. Okay, let us put all this in a tabular format. The tabular format is there for you to understand. This will help you in understanding. We have put all this together in a table that will summarize what is that we have studied so far in a DTFT. Now, let us see some examples on the board. So, what does this example say? It says find the discrete time Fourier transform of a discrete time signal given as gamma to the power of n, u of n, and also given is the gamma value is less than 1. So, let us put this and then let us try to solve this problem. Okay. The solution. Okay. So, first of all, DTFT of x of n is x of e to the power of j omega and is given by a summation n is equal to minus infinity to infinity x of n e to the power of minus j omega. Let us see this example. The example says you have to find out the discrete Fourier transform for a given signal x of n is equal to gamma to the power of n u of n. Okay. So, let us write the formula first. So, DFT of x of n is e to the power of j omega summation minus infinity plus infinity x of n e to the power of minus j omega. This is the formula which we know. Now, let us put on what we know. Okay. So, that is equal to n is equal to minus infinity to plus infinity gamma of n u of n e to the power of minus j omega n. Okay. Now, this u of n indicates that this exists only for positive values. So, can rewrite this as n is equal to 0 to infinity gamma to the power of n e to the power of minus j omega n. Okay. Let us take n common from this. So, I can write this as n is equal to 0 to infinity gamma e to the power of minus j omega n. So, this is a geometric progression with a common factor gamma is equal to e to the power of minus j omega. So, x of e to the power of j omega will be equal to 1 by 1 minus gamma e to the power of j omega. Okay. Then e to the power of minus j omega can be written in terms of cos and other functions. So, I can write this as 1 by 1 minus gamma into cos omega minus j sin omega. Okay, this I can take it common here. So, I can write this as 1 by 1 minus gamma cos omega plus j gamma sin omega. Okay, this is my x of e to the power of j omega. Okay, now I can find out the magnitude of this and also the phase of this. So, how do I get the magnitude of this? So, let us do it here. So, Let us write down here what is e to the power of j omega. So, the magnitude of this is given by 1 by 1 minus gamma cos omega whole square plus gamma square sin square omega. So, this I can write as 1 by 1 plus gamma square into cos square omega plus sin square omega, okay, minus 2 gamma cos omega. Okay. So, that is again you can write that as 1 by 1 plus gamma square minus 2 gamma cos omega. Okay, this is the magnitude. Similarly, I can calculate the phase of this. The phase angle of this is equal to minus tan inverse of omega sin omega multiplied by gamma by 1 minus gamma cos omega. So, this is the magnitude of this, this is the phase angle of this. So, we have calculated given at x of n discrete time signal equal to gamma to the power of n. We have calculated this given the condition that this must be equal to less than 1. So, gamma must be equal to less than 1, that is what is given condition. So, this is how we have calculated the discrete time Fourier transform of a given signal x of n is equal to gamma to the power of n u of n. So, the important point here is because u of n is given, we have changed the summation from 0 to infinity instead of minus infinity to plus infinity. Let us see an example 2. What does it say is, the figure below shows the discrete time signal, that is x of n is delta of n is given here. As you see here from the figure, is existing only for a value 0. Okay, x of n is having a value of 1, at 0 only it is existing. So, we have to find out just the discrete time Fourier transform. So, let us write down the formula first. So, the x of e to the power of j omega, which is nothing but the dt ft of x of n, that is given by summation n is equal to minus infinity to plus infinity x of n e to the power of minus j omega n. For us x of n is delta of n. So, let us rewrite that again. N is equal to minus infinity plus infinity delta of n e to the power of minus j omega n. Now, understand the shifting property of the delta function and also the fact that this whole summation exists only at one point, that is n is equal to 0, I can write this like this. So, this will become 1, now this is 1. So, what happens here is this will become e to the power of minus j omega n at n is equal to 0. So, that is this is equal to 1. So, how does the discrete time Fourier transform look like? So, this is my frequency spectrum, this is the value. So, this is x e to the power of j omega and this is my omega. So, this is an important pair which you already see in the form of a table. So, we are doing it here. A delta function given like this, when I transform it into frequency domain, this will be equal to 1 and this is how the spectrum looks like for different values. Let us say this is pi, 2 pi and this is minus pi, minus 2 pi and so on. This is how the discrete time Fourier transforms looks for a delta function which is existing at this particular function. Value of n is equal to 0 only. Let us see the third example. The third example says, determine the frequency response of a discrete time LTI system with impulse response h of n given as delta of n minus n naught. Also determine the output for this system. So, let us just put it on the board like this. Okay. So, this is my h of n and let us say this is my output y of n and this is having a input as x of n. So, the frequency response of a discrete time LTI system will be the discrete time Fourier transform of h of n. So, once I find out h of e to the power of j omega, which is the discrete time Fourier transform of h of n, I will get the frequency response of a system. So, let us say h of n is having a discrete Fourier transform x of e to the h e to the power of j omega. This let us say is having y e to the power of j omega and this is having a discrete time Fourier transform of x of e to the power of j omega. So, first of all, let us solve the first part. What does the first part say? We have to find out the frequency response of a discrete time LTS system, which is h of n is given. Now, h of n is given, I have to calculate h of e to the power of j omega. That gives me the discrete time Fourier transform. So, let us find out what is the h of e to the power of j omega. Okay, that will be equal to, again we use that formula, n is equal to minus infinity plus infinity, h of n e to the power of minus j omega n. Now, what is h of n for us? So, that will be equal to n is equal to minus infinity to plus infinity delta of n minus n naught e to the power of minus j omega n. So, using again the shifting property of the impulse response, of the impulse signal, what will be this answer? This will be equal to e to the power of minus j omega n naught. If you look at the previous problem, it was e to the power of minus j omega n at n is equal to 0. So, this is equal to e to the power of minus j omega n naught. Now, this is my frequency response. So, the first part has been calculated. I have found out what is the frequency response of my signal. So, this indicates, what does this indicate? This indicates that the magnitude spectrum of the frequency response of the system, which is LTI system, is 1, whereas the phase angle is minus omega n naught. That is the phase angle for all frequencies. So, that is clear now. Now, what is it I have to do? Now, I have to calculate what is the output for this system. So, how do you calculate output for the system? We said the output is represented by a by this function y of n. Okay, we are denoting y of n as the output of the system, which is having a discrete time Fourier transform of y is equal to of y e to the power of j omega. Now, y, this response will be equal to the product of these two. So, what will be y of e to the power of j omega, which is my output? So, this is equal to x of e to the power of j omega, okay, and h of e to the power of j omega. Okay, so, this is my output response of the system. What is y e to the power of j omega? What is our h? Our h is minus e to the power of minus j omega naught. So, we will write this here, e to the power of minus j n naught, okay, and x e to the power of j omega. Now, if you remember the time shifting property of dt of t, there is a delay of minus n naught. So, how do I get y of n? Y of n will be inverse discrete time Fourier transform of y of n, that is the output in time domain, is equal to inverse discrete Fourier transform of what? Y e to the power of j omega. So, from that property, what is the output now? This will be equal to x of n minus n naught. Okay. So, that means the input which we are giving to a system h of n, x of n we are giving, but what is the output? The output is x of n minus n naught, that is, it is delayed by a factor time or factor of time by n naught. That is what the significance of all this is. So, how we have done this problem? Let us just quickly summarize. So, what is that we have done? We have used two properties here. One is a convolution property and the second one is time shifting property. The first is, I want to calculate the frequency response of the system. The frequency response of the system is nothing but calculation of dt ft of the h of n. So, h of n for us is given as delta of n minus n naught, that is, by using shifting property I have calculated the frequency response. We said that for all frequencies the magnitude of this is 1, whereas the phase angle is shifted by a factor minus omega n naught. Then how to calculate the output of a system? The output of a system y of n is nothing but convolution of x of n and h of n. But in our problem we have already calculated x e to the power of j omega and we also calculated h e to the power of j omega. Once these two are known to us, it is very easy to calculate y of e to the power of j omega, that is a discrete time Fourier transform of y of n. That is what we have done. So, that is a product of these two. When I multiply in frequency domain, it will be convolution in the time domain. So, this is what we have done. So, inverse Fourier transform of it is simply y x of n minus n. Say here I have used the property time scaling. So, e to the power of minus j omega naught if you multiply, it is equal to delaying the signal x of n minus n naught. So, the impulse response delta of n minus n naught in fact is delaying the input signal by a factor of time n naught. Let us see example 4 now. Example 4 is, determine the impulse response h of n of a discrete time ideal low pass filter whose frequency h of e to the power of j omega is shown in the figure here. So, if you look at this figure, this is the frequency response of an ideal low pass filter. So, it says response of the system is like this and is existing between omega c and minus omega c with an amplitude equal to 1. Now, we have to calculate the response. How do I calculate the impulse response h of n? So, h of e to the power of j omega is n is given. So, what we have to find out is h of n. That means, if I calculate the inverse discrete time Fourier transform for this signal, I will get h of n. So, we already seen what is the formula. We already seen what is the formula for h of n, that is inverse discrete time Fourier transform h omega. We will write that and let us integrate this and then let us find out what is the impulse response h of n for a given response for a filter. So, let us do this now. Okay. So, how do I get h of n now? H of n is nothing but my inverse discrete time Fourier transform given by this formula 1 by 2 pi existing between minus pi to plus pi h of e to the power of j omega, okay, e to the power of j omega d omega. Okay. So, the formula is h of n is 1 by 2 pi minus pi to plus pi h of e to the power of j omega e to the power of j omega n d omega. So, this is the formula. Now, let us substitute what we have. Now, what we have is, let us say for us the function is 1 by 2 pi, there is a period of the signal and is existing between minus omega c to plus omega c. So, let us put minus omega c here and plus omega c here. Okay. And what is the h of e to the power j omega for us? It is 1, okay, e to the power of j omega n d omega. So, let us do this integration. So, that will be equal to 1 by 2 pi into 1 by j n e to the power of j omega n, which is existing from minus omega c to plus omega c. 1 by 2 pi, okay, we will bring this out, 2 pi n, okay, then this is equal to e to the power of j omega n existing from minus omega c to plus omega c. Okay. Let us substitute this now. Now, let us put this here and do this. So, that will be equal to h of n now will be equal to 1 by j 2 pi n. Okay. So, this will be equal to e to the power of j n omega c minus e to the power of minus j n omega c, okay, j to the power of n omega c. So, this what I will do is I will push this j2 inside. So, that will be equal to 1 by pi n e to the power of j n omega c minus e to the power of minus j n omega c by 2j. Okay. So, this is nothing but sine n omega c. So, this I can write as sine n omega c divided by pi. So, this is our value for h of n. Okay, that will be equal to sine n omega c by n pi.